This is A21 June 2010 question 5. The equation is shown for the nuclear radius r is equal to r0 a to the third. What do the following terms in equation 5.1 represent? So there's two very easy marks. R0 is the radius of a nucleon, and A is atomic mass number, or you could say the number of protons and the number of neutrons. On figure 5.1, sketch the shape of the graph expected for equation 5.1, given the axis is labelled on figure 5.1. So we've got r versus a to the third. Now if you look at the relationship up there, r is equal to r0 a to the third. That means r is directly proportional to a to the third. And so if you plot values of a to the third and r on the two axes, you're going to get a straight line which goes through the origin. And this would be a common enough question too, so it's definitely worth your while having a look at that and remember what it is. So it gives you a nice straight line through the origin. Explain how to find a value for r0 from the graph you sketched in figure 5.1. So if I just write down the equation here again, r is equal to r0 a to the 1/3, and then y is equal to mx beneath it. We've got y, r on our y-axis, and x, we've got a to the third on the x-axis, and therefore r0 is just the gradient of the graph, and that's certainly worth a guess. Now you just need to be careful just in case the two axes are plotted the other way round, and then you would have to make sure that you would be taking 1 over the gradient if that was the case. But in this case it's very straightforward. The radius of a nucleon can be found from the gradient of the graph. Part C, show that the nuclear radius of gold is 5.73, sorry that's silver isn't it, it's 5.73 femtometers if r0 equals 1.2 femtometer. Now you need to know that 1 femtometer is 1 by 10 to the minus 15. You should have a good idea of the radius of a nucleus anyway. So you're just going to use your equation r is equal to r0 a to the third, and that's equal to 1.2 by 10 to the minus 15 times the atomic mass number is the big number at the top, which is 109 to the power of a third. And that gives you an answer of 5.73 by 10 to the minus 15, which is what you expect because that's what you're trying to show. Calculate the nuclear density of silver. The volume of a sphere is 4/3 pi r cubed. So density is mass over volume. The mass of the silver is its atomic mass number multiplied by the mass of a proton. So it's A times m, mass of a proton, and it's all over 4/3 pi r cubed, and r is the number that you calculated above. And so atomic mass number there is 109, and it's multiplied by 1.66 by 10 to the minus 27. You of course get that in your booklet, your atomic, the mass of a proton. And that's divided by 4/3 times pi times 5.73 by 10 to the minus 15 cubed. And that gives you an answer of 2.30 by 10 to the 17. And you always expect a very, very big number by 10 to the 17 or so for the nuclear density of the nucleus. And then, of course, the next question always is comment on the nuclear density of maybe either the nucleus compared to ordinary matter, or in this case it's actually the nuclear density of selenium compared to silver, which are two metals, and explain your reasoning. So it tells you that metallic silver has an ordinary density of, you know, the actual material, not the nucleus, of 10.5 by 10 to the 3, and another metal, selenium, has a density less than half of that at 4.8 by 10 to the 3. Comment on the nuclear density and explain your reasoning. Now, no matter what, nuclear densities are always the same or very, very similar. And the reason, I'm going to write down the answer. Similar densities. And the reason is because the density is independent of the atomic number, mass number. So these two metals, they're not giving you any information about atomic mass numbers, but they will definitely have different atomic mass numbers. But just to show you why the density is independent of the atomic mass number A, density is mass over volume, and mass we discussed there was the atomic mass number multiplied by the mass of a proton. Now that's over 4/3 pi, and pi is times r cubed, but the radius of a nucleus is, of course, from our equation r0 a to the 1/3 cubed. And if you cube that bottom row, you end up with a times the mass of the proton over 4/3 pi r0 cubed, and then a to the third times cubed just gives you a, and the a's cancel each other out. So the density of any metals, the density of the nucleus of any metal should be the same, because it depends only on the mass of the proton and the the radius of a nucleon, which is constant, and therefore they should be the same. You don't have to show all this as long as you are stating that and stating this, but this is just understanding that. This is just a wee explanation of it.